we start now?
It's
Yeah, I guess we will. Okay, so welcome back, everyone. So my name is Chris Boily from University of Strasbourg, and this afternoon's session is actually the last formal session for this meeting. And for our first speaker this afternoon is Shin Rong from Taiwan University, National Taiwan University, and University of Illinois in the US. And she will give us a talk about libyt. So it's a 15-minute talk plus 5 minutes presentation discussion, starting now. The floor is yours.
Today I'm going to share about libyt, a tool for in-situ parallel analysis and its scientific applications. This is more about the computational aspect in simulation in astrophysics. And I am Shin Rong, and this work is done together by Xiyu and Matthew. So I will quickly go through why do we want to develop this tool and how do we do this, and demonstrate the procedure of implementing libyt in simulation. And I will show some production run and close with discussion and conclusion. So why do we develop this tool? So normally, if we want to analyze simulation data using Python, we need to output data to local disk first, and then use Python to analyze them. And sometimes this requires load data back to memory. So we want to skip this write data to local disk process and analyze them directly in memory while simulation is still in runtime. So we developed this tool, the libyt, which is a C++ library for YT, to connect simulation and Python. YT is a Python package for analyzing and visualizing volumetric data. And so this way, we only need to store our interested target result on the disk. So this reduces disk usage and can help us increase the temporal resolution of simulations. So a brief view about libyt. Libyt is the middle layer that handles data I/O between simulations and Python. And if we launch the simulation code in an MPI process, each MPI process contains one simulation, one libyt, and one Python instance. And these Python instances will work together to conduct in-situ analysis. And since YT supports parallelism feature already, we directly borrowed this Hall feature. So these are some YT functionalities we've tested, and it actually worked in in-situ analysis. And basically, we support all of them, even other Python models, so that you can actually call other Python models other than YT in in-situ analysis using libyt, though there are some limitations. So unlike post-processing, where data is stored on disk and every MPI rank can access these data whenever they want, in in-situ analysis, data is separated in different MPI process, and there is no guarantee that each Python instance only need to deal with local data, because this depends on the Python script you run during the analysis. And we use one-sided MPI, or so-called remote memory access, to solve this problem. So in one-sided MPI, each rank will put other ranks' desired data into their shared memory, and each MPI process will access and fetch the data they required, but it's located on other MPI rings during this epoch. Yeah, so we no longer need to determine how should each MPI process do the point-to-point communication and handshaking with each other. But the way we implement this data exchange process force each rank must enter the data IO stage at the same time, because there are some collective one-sided MPI calls we use during this process. Yeah, so every rank must participate in it. Yeah, so how do we support the adaptive mass refinement code base? We create another structure for storing hierarchy data and field data. And we pass, each MPI rank only has to pass in local hierarchies like left edge, right edge, and level, parent ID, etc. And also pass in the local field data. And libyt will gather these local hierarchy in different MPI rings, and then combine them to full hierarchy and load them into Python, so that each rank will contain the full hierarchy. And for local field data, libyt use NumPy API to wrap these data and tells Python how to interpret this block of memory, which contains those field data. And this step does not require additional memory, because Python is now directly reading and using the simulation data. And we also support derived field. Derived field are field not ready for YT yet. For example, face-centered magnetic field data, which requires us to convert it to cell-centered data. And these kind of data either need manipulation or does not even exist yet. libyt looks for user input function to generate these data, and it only prepares these data when YT needs them, so that it saves memory. And some examples are like face-centered magnetic field data to cell-centered, and we can also derive temperature field through equation state of routine, which are some routines already implemented in some simulations. Yeah, so when Python needs these kind of data, it asks the YT Python model for data, and then this module will allocate a new array and call the function pointer passed in by users. And this function generates the data the Python wants, and then pass back to the libyt. And the libyt will wrap them to NumPy array and return the data back to Python. Yeah. And we also support particle data. Particle data are discrete and are discontinuous in memory space, so we cannot wrap them using NumPy API. And we use the same method as in solving derived field, which is to use the input function pointer by user and use it to gather particle data and generate them when YT needs it. Yeah, this is the same procedure like in derived field. And this is our the final form of libyt, which requires us to prepare the data to connect simulation data to Python and called in-situ analysis, which is to run the Python function already defined in the script and then free them when we are done and use libyt to analyze them. And this is these two are this is post-processing script and in-situ analysis. And the only difference is that they load data. One is load from disk and one load from memory. We already implement libyt inside Gamer, and one of our production run, which is wave dark matter vortices. The goal of this simulation is to observe the density neural lines and their evolutions during some time period at the center of the halo. The ratio of the simulation domain to target is 100 to 1. And yeah, so every time step takes 116 gigabytes, and it needs total of 300 more steps to see the evolution clearly. And if we use post-processing, this is unrealistic. And so we use the libyt tool to extract our target region into uniform grids. And then use other tools to compute density field to density neural lines, and then visualize in ParaView. And this is the forensic green line is the density neural line. And if we zoom into these forensic line, you can see there's interference pattern, and it is in such high resolution, both high resolution in time and space. So we can see the pattern clearly. And this is another run, which is core collapse supernova. And this is the slice plot of entropy. And the center is neutron star, and you can see the advection region. Yeah, so the performance of using libyt is generally faster than using post-processing, which is load, which is how normally you would use Python under the same environment, which is using same MPI processors. Because we load in-situ analysis, load data from memory, not from disk. And they also have the they have similar scalability because libyt directly borrows the whole YT parallelism feature. Yeah, so some limitations of libyt, and because due to the synchronous data exchange process in libyt, we forced each MPI ring to participate in data exchange process, which is every Python needs to enter this data IO stage. So if not, we cannot do this in-situ analysis. The process will hang. So some limitations like for volume rendering to run, we have to use even MPI size environment. And also currently libyt only supports C++ simulation code and using adaptive mesh refinement structured only. And we hope we can support more code base and other formats like using particle code base. And there is no extra time needed when we use libyt to do the in-situ analysis, and converting the post-processing Python script to inline analysis script is easy. So I think libyt provides another way for researchers to interact with data and analyzing large simulations in a high temporal resolution feasible. Yeah, and thank you. That is the end of my talk.
Right, thank you very much. This sounds like a very promising approach. There's time for questions. Actually, we have time on our hands. If you want to raise your hand, maybe I see that Jonathan has raised his hand. Jonathan, if you want to.
Yeah, sure. Hi. Thanks very much for the presentation. It was great. I was wondering could you comment on how much work it would be to connect libyt to a new simulation code?
Oh, I think it wouldn't be hard. Yeah. I've read the documentation, and I think it should be easy where you just set parameters like length and unit, etc. And yeah, load your fields. What fields do you have, like density, momentum in x direction, and particle, and load grid hierarchy. Yeah, just basically you just load information in adaptive mesh refinement structure, and the work is done. I mean,
Okay, is there like a template for which simulation code you've used as a test for this?
Yes, there's an example under the libyt, this repository, and also there's example under gamer simulations.
Okay, great. Thanks very much. Looks very interesting.
Any more questions, or should I field one question of my own, perhaps? Does that then require any kind of code hacking to at least force the synchronicity between the different ranks? Because if I understood, you still require to have like an MPI data sharing, so you have to block your communications at some point to synchronize the code. So does that actually require still a minimum of hacking in the codes to at least link to the library?
There are some other structures. Yeah, because currently because there is no like client and server structure in our implementation of this libyt. So and because each rank are doing are like compute their own stuff, so there is no way like each rank, there's no way for each rank to know what others needed. And yeah, so
Yeah.
they must like gather all the information together under this kind of this libyt structure, because there are no client and server node to control of this process.
Okay. Any more questions to put to? So it is Shin Rong, no? Shin Rong. Sorry.
Yes.
Anyone want to ask a question, or perhaps I guess in the link would be important to see that link in the Slack. Actually, the Slack is going to be very useful for that. If you have a GitHub repository, then be sure to make just copy the link directly after your talk in the Slack. and people will then access that. It sounds like a very promising approach to data analysis. So thank you very much. If there are no more questions, I think we should move on perhaps to the next speaker. So thanks again for